Can people hear me? Yes? Okay, great. Well, thank you so much for inviting me. It's really great to be here. I've had some really good conversations this morning already on topics that I'm not so familiar with. So it's always, I think, really fun to talk to a different kind of audience. So I look forward to your questions and feedback. I'll probably give my talk for about, 50 minutes or so. And if you have clarification questions, you can raise them. Otherwise, maybe we'll hold the questions and discussion after the talk. Okay. But I will try to be a little bit sort of informal because I know most of you are not psychologists. So if anything sounds strange, unfamiliar, or unclear, please do let me know. All right. Okay. So I am somebody who studies early cognitive development with infants and young children mostly. I want to begin by just talking a little bit about sort of various views about what is it like to be a baby. And these are probably things you're already pretty familiar with, just some of the things that you've heard in the literature. So William James talked about one great blooming, buzzing confusion as a way of characterizing the infant's starting state. And John Locke and others have talked about sensory experiences as being sort of at the beginning of life. And that's what we start with, and then we build up from there. And of course, Piaget talked about sensorimotor intelligence as a way of thinking about the first couple years of life, and out of sight, out of mind. It's literally true of young human infants. Philosophers have talked about this idea. Coyne, in particular, talk about how for infants, their world does not consist of individuated entities they can keep track of over time and space. So they think of the world as more mama, more milk, and more bottle. And on the more nativist side, Jerry Fodor, a philosopher, made the radical claim that all concepts are innate, including a carburetor. I have to confess, I still don't know what carburetors are. If you look at the kind of mechanism people have looked at in recent years, one very prominent view is this idea that infants can keep track of a lot of associations and correlations, and that's one way of propelling development forward. So this is just a quick survey of some of the views that are already out there. And roughly speaking, they can be divided into two camps, which again, I'm sure you're familiar with. So there's the nativist view, where people talk about rich initial knowledge and conceptual primitives. And development is perhaps largely enrichment. There's a lot of continuity starting from infancy on. And also there's also a lot of talk of domain and specificity, even in very early points of development. And on the other side, there's the empiricist view, where the hypothesis is that infants start with a set of perceptual primitives, and associative learning mechanisms are largely responsible for kind of learning and development you see over time. And there's quite a bit of discontinuity if you look at the course of development from infancy through late childhood. And also there's a lot of talk of domain general learning, where there's a set of domain general mechanisms that are responsible for the development we see over time. Okay. One way to think about some of the debates that's been ongoing for some time is there appears to be a little bit of a sort of impasse, right? So on the one hand, we know that young children acquire knowledge and concepts quite rapidly, especially over the first few years of life. So if you look at work in cognitive development from the last couple of decades now, you see that infants are getting smarter and smarter, as it were. So there is a lot of demonstrations of early competence, various sorts in different domains, understanding objects, understanding agents, understanding maybe the really basic moral concepts like helping and hindering. On the other side, you have these sort of slow, laborious associative learning mechanisms that are not really sort of up to the task of explaining why knowledge acquisition, in fact, takes place very rapidly during the first few years of life, right? At least that's what researchers have been debating about for some time. And when you think about the nativist views, there's also sort of the, if you like, the poverty of the imagination kind of argument. So if we can't think of mechanisms that are responsible for the learning we see, the knowledge and the concepts must be innate. So neither side is particularly satisfied with the state of affairs. And then if you look at some of the work that's been going on for the last decade also, and there's sort of a whole a growing body of research suggesting that what we think of learning, the nature of learning in infants and children, perhaps that view needs to be revised quite heavily. So early learning is much more sophisticated than previously thought. Examples are from language development, in particular, early language development, speech segmentation being a prime example that probably many of you are familiar with. And there's work in physical reasoning and other domains, in causal reasoning, showing that young children are very good at taking small amounts of data and making the kind of leap that seems necessary to propel knowledge acquisition to proceed very quickly. So many of us want to suggest that these young learners are sort of experts at inductive learning and statistical inference. That is, they can make principled and meaningful generalizations given limited amounts of data. So that's going to be the focus of this talk, trying to get some handle on what these statistical and inferential mechanisms are that we seem to have some evidence for these days. So my colleagues, collaborators, students, and I have been trying to advocate for what we call a rational constructivist approach to study of development in recent years. We hope it's not just a new name, but rather it comes with a set of basic claims. Probably the most important one is this idea that early learning mechanisms are perhaps best categorized as rational, statistical, and inferential. And we'll get into what those terms mean in a second. And learners can combine prior knowledge and input statistics in principled ways. And lastly, we want to suggest perhaps some of these domain general mechanisms can give rise to domain-specific knowledge as we see later on in development. So what's meant by rational? As a first approximation, we are adopting a sort of a Bayesian inference framework where learners can integrate prior beliefs and new evidence in the principled rational way. And again, to a first approximation, you can think of Bayes' rule as a way of capturing that phenomenon, where the learner is trying to assess the probability, the posterior probability of a hypothesis given a set of data by taking into account the prior probability of a set of hypotheses and also the likelihood, which is how likely you're going to see the data given this set of hypotheses. Right. Furthermore, we're operating under the assumption that the learners are trying to build generative models of the world. Right? So this is not a learner that's just keeping track of associations and correlations, but rather they're building causal models of the world, and they're developing ultimately intuitive theories about what's going on around them. They can reason about how evidence is generated. We see some empirical work trying to focus on that aspect of things, and they can make inferences accordingly. And they perhaps can evaluate the strength of the evidence against multiple hypotheses in some cases.
Just clarification, yes. How is the prior, the original prior set?
There are some prior, there's definitely some amount of prior knowledge and probably biases going into the game, if you like. Right? So our perceptual systems are constrained in certain ways, such that perhaps you're more likely to pick out coherent bodies, even though you don't know anything about them. And you're maybe looking for correlated perceptual features to distinguish animate objects from inanimate objects, for example. So I think some of these things are already built in, right? But I think I think it's an open question whether you can think of these as really conceptual primitives or maybe something a little bit weaker. But I'm happy to return to that point in the discussion. All right. Okay. What is meant by constructivist? So constructivist views are not strangers to developmental psychologists. In fact, if you look at some of the work that Scott Johnson's lab has been doing in the last number of years, you can see lots of elements that are, I think we will call constructivist views of development. So here, I want to emphasize just a couple of things. One is these mechanisms of inference and inductive learning will allow the learner to construct new knowledge and concepts and learning biases. And they can acquire these new learning biases. So I'm appealing to this idea of learning to learn that's been in the cognitive psychology literature for some time. That is, learners can use the initial input to kind of figure out how the world works, and then these newly learned biases could guide them in subsequent learning. They could revise their beliefs and hypotheses as they go along. And last but not least, I think this is a key element of the constructivist view, that the learners are quite active in terms of being engaged in the learning process. Okay, so the main claim is that infants and young children, even from they're very early in development, are these powerful, rational, constructivist learners. So what's the state of the evidence? So the rest of the talk will basically focusing on the empirical work we've been doing in the last 70, 90 years or so, looking at whether infants and young children are rational learners and whether infants and young children are constructivist learners. So I will start by looking at some studies we've done trying to address the issue of whether infants have some ability to kind of, if you like, behave like little intuitive statisticians, right? Whether they can do some of the really rudimentary things that we learn to do as undergraduates and graduate students in our stats classes. But furthermore, I want to ask the question whether they can integrate some prior knowledge into their statistical computations, important part of the Bayesian framework. And I will talk about a study where we asked them to make some predictions in their action task. And lastly, I will give one example to show some domain specificity of these mechanisms. Okay, so we'll start by asking whether infants are sort of little intuitive statisticians. So I want to imagine a jar full of jelly beans. This is basically the philosopher's urn, except they talk about jelly beans with babies. So if you don't know what the content is in the jar, and you close your eyes and pull out a bunch of jelly beans, and what you see is there are a whole bunch of red ones and a few white ones. Right? And if I were to ask you to guess what's inside the big jelly bean jar, you're probably going to say, oh, chances are it's going to be a lot of red ones and some white ones. Maybe there's some other colors, but you have missed something. Right? But you have some guess, given the sample you've seen, as to what is likely to be in the big jelly bean jar. So we basically ask these 8-month-old infants the same sort of question. So this is a looking time task. I hope the method is pretty familiar to most of you. So basically, infant is sitting more or less where you're sitting and watching some events unfold on a puppet stage. The room is darkened so we can focus on the stage. The stage is lit. And in most of our studies, at least the ones I will talk about, there is a live experimenter who's presenting the displays. And other labs use computer-generated displays, and we use those sometimes as well for better stimulus control. But it is more engaging for young infants, most often than not, that if it's a live performer, if you like, that's presenting the objects to them. So I will show the video for the procedure. I think it's pretty straightforward, and you can get a sense of what the babies watch. So there's a big box, and the experimenter shakes it, This is from a vision trial where we just show them, okay, sometimes the box has lots of red balls, other times it has a lot of white balls and a few red ones. You can't tell by looking at the box which one it is. Now the box is closed again. She's closing her eyes, pulling out some ping pong balls one at a time.
This one. Look at this. See that one? Look at this one. Look, baby, look.
So every time they're looking, the video is edited, obviously we'll wait till the baby is away. On a different trial, a closed box is presented again, so they don't know what's inside. And the experimenter again draws out a bunch of balls with her eyes closed.
See that one? Look at this. Look at that one. Look, baby, look.
So hopefully you're surprised at this point. It's very improbable, not impossible, but improbable for you to have drawn a random sample and looks like that, right? It's statistically speaking, it's just a low probability event. It's not impossible. It could obviously happen, right? But nevertheless, we notice that quite quickly, and we kind of go, that's kind of weird, right? Whereas obviously with the previous sample with 4 red and 1 white, you go, oh, okay, of course, then you just draw a bunch of balls and it looks like that, right? Given the population in the box. So we measure infants' booking times, contrasting these two kinds of test trials. And the 8-month-olds, okay, so it's just a quick review of the probable versus improbable outcomes. We showed them one at a time on alternate trials. And if you look at the first set of bars, that's the first experiment. We ran a set of 8-month-old infants. And we found that they, on average, they looked reliably longer at the improbable outcome than the probable outcome. Just like you would have if I had in fact measured your booking time, right? You kind of took it, you got a double take, and you probably would stare longer at it, thinking, okay, there must have been a trick or something, right? So that's a rationale we're trying to capture from these infants. These methods have been used quite a bit in the literature. And the second set of bars as a replication with a different group of infants, just to make sure that the finding is robust. And some of you might be thinking, okay, you want to argue that the baby is really smart. They're looking at what's in the sample and what's in the box and kind of comparing them and thinking about what's probable and what's improbable. But maybe there's a much more low-level, less interesting explanation, which is that they look at what's in the small container and what's in the big box. If there's a mismatch, right? So if there's a lot of white over here, there's a lot of red over here, that's interesting, right? We know this kind of perceptual effect exists, but if you see lots of red over here, lots of red over here, who cares, right? So maybe the babies aren't that smart, they're just responding to the features of the perceptual array. So we ran a version of the study as a control, where instead of the experimenter pulling out the ping pong balls with her eyes closed out of the box, she pulled them out of her pocket, right? So there's no relationship between what you see in the small container and what's in the big box, right? But of course, the final outcomes are exactly the same in the two cases, right? And as you can see, in the third set of bars, the effect goes away. So they think they're, all medium level, interesting, whatever, right? There's no difference between the two kinds of outcomes, right? Suggesting to us that the babies had thought about the fact that what you see in the small container is related, is causally related to what is presented in the big box, right? And they're sort of thinking, okay, maybe one of them is a little bit unusual and improbable than the other, just like most of you did, right? And since then, both in my lab, also other labs, people have used different variants of this kind of method. Taglos Bonatti used sort of a single event probability case. They had a lottery machine. You might have seen the PNAS paper they published a few years ago, where there's one blue object and 3 yellow objects, and they're just bouncing around in the lottery machine. And at one point, the lottery machine is covered, and one object exits the machine. Right? So the question is, would the infants look longer if it's the rare object, the blue one that exited, as opposed to the yellow one? And they found conversion evidence with 12-month-olds. Okay. And Stephanie Dennison, a former graduate student in my lab, also tested using a variant of the method with 6-month-olds and getting positive results. So there's been various replications in the literature suggesting that during the second half of the first year, we tried 4-month-olds, by the way. It didn't really work very well. So it's possible that, in fact, it kicks in right around 6 months of age. So during this first half, the second half of the first year, we're seeing some evidence that infants are sensitive to these sort of probabilistic relations, and they can make these simple inferences based on samples, populations. And in one case, we looked at the converse as well. All right. And we wanted to ask the question whether infants can integrate prior knowledge in their statistical inference. It's an important issue to address, partly because infants are already kind of knowledgeable during the second half of the first year. So there's lots of demonstrations. They've got quite a bit of physical knowledge about small, medium-sized objects. And they're also beginning to acquire psychological knowledge about how agents behave. Okay. And we're interested in this question partly because the framework, in fact, suggests that prior knowledge should be integrated in a rational way. And so we want to put that to an empirical test. So we started by asking slightly older infants, 11-month-olds, because the task is a little bit more difficult, whether they can integrate psychological constraints, in this case, a goal or preference and visual access in their inferential mechanism. So there are 3 groups of infants in this study. And just quickly to go back to your imaginary jar of jelly beans, basically this is a case where somebody pulls out a bunch of red jelly beans from the jar, but you also know, Sally, the person who just performed this action, really likes red jelly beans, and she looked inside the jar when she's pulling them out, right? So that basically cancels out the assumption that this is a case of random sampling. Instead, you might think, her likes is the driving force behind when you actually see her pulling out of the jelly bean jar. Okay. So that's, in effect, the study we did with infants. So in some cases, the experimenter basically shows the infant that she likes red ping pong balls. So initially, there's a little container with 3 red balls and 3 white balls and 3 red balls, and the experimenter basically keeps picking out the red ping pong balls and never the white ones. Right. So anybody watching this event could just say, oh, okay, maybe she likes the red ones, or maybe she wants to pull out the red ones, etc. And then in the sampler condition, she has visual access. She looks inside the box while she's pulling out the balls. Okay. And she gets out either 5 red ones or 5 white ones. And in another case, it's a little more complicated. Even though the experimenter expresses her goal or preference for the red ping pong balls, she's blindfolded when she's pulling out balls from the big box. So she can no longer control what she gets out of the box. Okay. So we want to see if the infants can kind of understand some of these more subtle manipulations. So again, just back to the design, 3 conditions. The first one is essentially a replication of the study you just saw with 8-month-olds. Right? So there's no goal, there's no visual access, so basically the statistical property should dictate what you get. The second case is the case where the experimenter expresses a goal of picking up just the red balls, and she has visual access of sampling. So we are predicting that her goal or preference would be the driving force behind it. And lastly is the case where there's a goal, there's preference, but there's no visual access. So the prediction is the box content should drive the looking time patterns. All right, so these are the data from the 11-month-olds. And in the random sampling condition, this is a replication of the earlier finding. The infants are looking on average longer at the improbable outcome than the probable outcome. I'm plotting this goal-directed sampling condition a little bit funny. That is, I'm going with the goal itself. So if the experimenter expressed a goal for red ping pong balls, then if she pulled out only white ones, that's the improbable case, right? So the effect is in fact driven by her goal and not by the proportions inside the box, right? In fact, if you plot the data the other way, it doesn't work. Okay. And lastly, when the experimenter expressed the goal for just picking out the red ping pong balls, but then she was blindfolded, so there's no visual access, then it basically reverts back to a random sampling case. And the looking time reflected that they again look longer at the improbable outcome when it's based on the proportions inside the box. So at this point, it seems that the 11-month-old infants already have some ability to say, okay, this is not just some pure bottom-up kind of process, but rather I can keep track of what the experimenter is liking or likes and dislikes, and whether she has visual access or not during the sampling process. Right? These are all relevant factors in my statistical computations. Okay. Then we turn our attention to a case of physical constraints. Again, a 1-year-old already have quite a bit of physical knowledge, as we've seen just looking at the work on physical reasoning and object concept for the last couple of decades. And this is a case where we create a situation where some balls are stuck inside the box, right? And the question is whether the infants can take into account that piece of information that we teach them sort of on the spot, right? So if you think about the jelly bean jar, it's basically a case where you understand that some of the jelly beans have been sitting in the jar for a long time, maybe they're already stuck on the bottom, so they're not available for sampling. So that's the intuition we're trying to tap into in this set of experiments. Okay, so we want to teach the child that some of these bars are stuck. So we actually did it several times just to kind of hit them over the head that there is a physical constraint in place here, right? And there are two conditions. One is where we introduce a probabilistic physical constraint, where they see that all the red balls can move freely, and only a minority of the green ones can move freely. Right? This is just experimenter picking up the balls one at a time to show them whether it moves or not. In the deterministic physical constraint condition, again, all the red balls can move, but none of the green balls can move. Okay. All right. And the test trials were identical in the two cases. You're showing them either a mostly green sample or mostly red sample. Okay. All right. So let me just go back to the design for a second. If you think about the probabilistic physical constraint case, even though the box content looks something like this, lots of green balls and maybe 20% red ones or something. But if most of the green balls are not available for sampling, this is what you should be thinking about, right? So in fact, there are many more red balls available for sampling, and then we have a very small, tiny proportion of the green ones are available for sampling, right? So in that case, you should think that the mostly red sample is the more probable one, and the mostly green one is the more improbable one. In the case of the deterministic physical constraint, none of the green balls was available for sampling. So even though the box looked like that, you should be thinking that, right? That really there's just a bunch of red balls inside the box available for sampling. In which case you might think both of these outcomes are improbable. Right? Okay. So if you look at these, again, 11-month-old infants' looking time patterns, what you find is in the probabilistic condition, they look longer at the mostly green sample as opposed to the mostly red sample, suggesting they had taken into account the constraint we had introduced at the beginning. In the deterministic case, when none of the green balls was available for sampling, they, in fact, on average, had elevated looking times for both outcomes, right? Suggesting that maybe they found both outcomes unsurprising since none of the green ones were movable and available for sampling. It's just the red ones, right? So even pulling out one green one is kind of surprising. So we want to use these results as evidence that towards the end of the first year, we already have some indication that infants are pretty sophisticated in using their statistical inference mechanisms. So they're not just blindly keeping track of the frequencies and the probabilities looking at boxes of objects, but instead they can integrate psychological constraints and physical constraints in their statistical computations. And there's some convergence evidence from Teglis and Bonati's group as well. Okay. For people who are familiar with the infant cognition literature, you know there's been a sort of ongoing debate about whether the kind of competence we see in young infants that's revealed by these looking time methods really give us some sense of how robust the representations are, right? Whether the representations are strong enough for making predictions and guiding action. So we took it upon ourselves, the infant researchers, trying to see if, as soon as we can get infants to make a choice or make a response, whether we can get them to think about, to estimate probabilities and use that to, as you can see in the study, to sort of navigate their own environment to their advantage, as a matter of fact. So now, if you imagine you're a kid at the mall and there are two gumball machines right in front of you, you have exactly 1 quarter, and you have to decide where to put your precious quarter to get one green gumball that you really, really like, right? So if you look at what's inside each of the gumball machines, there are in fact the same number of green gumballs in there. But if you look at what else is in the gumball machine, you see one has many, many purple gumballs, the other one has some purple gumballs, but not so many, right? So proportionally, you have a better odd, your odds are better in getting a green gumball from the gumball machine on the left than the one on the right, right? So you might decide that's where you should put your precious quarter. So we devised a version of this study with 10 to 14-month-olds. And instead of using gumballs and quarters, we used objects that look a little bit like lollipops. Again, I will show you the procedure. Easiest way.
Ellie? What are we going to do? No.
So Steph shows the baby 2 lollipop. One is pink and lights up, so very, very interesting. The other one is black and kind of dull, not very interesting.
See? I know.
So this is a preference
Go
trial.
get one, Ellie?
We'll just get them to crawl to one or the other.
Good
Make one of them much more interesting because we want them to have
You're
a strong
so good
preference.
at that. Yes, I am. Can I see it? Girl, want to see Mom?
That's always the most difficult part of the study.
Good girl. She's going to hide it. See?
Then she shows the baby 2 opaque cups with covers.
Wow.
And then 2 lollipop.
You see that?
The different mix is pink and black. That's their gumball machine.
Hey, Ellie. They're going to go away. Bye-bye. Close our eyes. Ellie, I got something.
So we can see the stick, so you know it's just one lollipop. She puts it in one of the containers, puts it up.
And Ellie, I'm going to close
So
my
it's
eyes.
another one.
Ellie, I got something. It goes there. Ellie, what do you think? You want to go get one? Good girl. Very good. You're doing great. She's doing fantastic. See? Yeah. See?
So this is a post-test.
Ellie, see? See, Ellie. There they go. Good girl. You're too good.
So we just want to make sure these have the same preference as the one that showed at the beginning. So we didn't, give them the chance to open the cup to see the lollipop. Okay. So so these are again 1-year-olds, and very quickly, it should be straightforward. We give the preference trial where they can crawl to one or the other. Most of them go to the pink one, as you can imagine. That one is bright and has stars and it lights up. And then there's a sampling event where they see something hidden being put into one of the 2 small cups, and then they can make a choice between the 2. And the assumption is that the baby is trying to say, okay, I really like the pink one, and I want to maximize my chances. So which one is more likely to deliver a pink lollipop between those two cups, right? Given the proportions I've seen in the jars, right? And what you find is that in the first study, about 3/4 of the infants crawl to the correct location, the one that's consistent with their preference is more likely to give them the pink lollipop that they preferred to begin with. And we've done several versions of the study since. And this is a version that's a little more difficult, where when you look at your two gumball machines, one has twice as many green gumballs than the other one. That's one you like. But unfortunately, proportionally, it's less in your favor to go to the one to put your precious quarter in the one on the right as opposed to the left, because proportionally it's still better to go put your quarter in the left to get the green gumball. Okay, so we basically did that study with the lollipops in the jars and the same procedure as you saw before, and about 80% of the children crawled to the correct location, where you look at the proportions of the two kinds of lollipops, it's more likely to deliver a pink one that they preferred than a black one. Okay. So one argue that infants' probability estimates are already pretty strong, even towards the end of the first year, and is strong enough to support prediction and action in the task I just showed you. And furthermore, infants seem to be spontaneously assessing the probability of outcomes and events, right? And they can use that knowledge to fulfill their own desires and wishes, at least in the simple task that we just demonstrated that. All right. So I want to turn to a different study where we're going to look at a slightly different phenomenon, but in a different realm, namely social cognition. So this is a case where we want to ask whether violations of random sampling in computing physical probabilities can actually be a cue for the child to say, okay, maybe I need to posit a psychological variable such as preferences, goals, or beliefs. Right? We tested, this is work with Tamara Kushnir, who's on the faculty at Cornell. And it's really her and Henry Wellman who got interested in this set of questions. We started with testing 3 and 4-year-olds, and then we did a version study with younger infants. These are 20-month-olds, the toddlers. So this is a study where there are two groups of children being tested, one in the 82% condition, the other one is 18% condition. There are no tricks in this case. So basically the toddlers are being shown a big box of toys. And there are always two kinds. Here they're depicted with triangles and circles, and in reality they're like toy frogs and toy ducks and things like that. Right? So in one case, there are lots of toy frogs and a few toy ducks. And the other case is the converse of that. There are lots of toy ducks and a few toy frogs. Right? And a puppet comes in, so this is agent, and he looks inside the box, and everybody can see everything, but nothing hidden, no tricks in the study. And the puppet will just reach in and pull out 5 toy frogs. Okay, in all cases, right? So that's the 5 circles. And at the end, we simply ask the child. We give them 3 objects: the toy frog, the toy duck, and a distractor, and we just ask them to give the agent the one that he likes. Okay. Now, if you imagine yourself in the study, if I pull out 5 toy frogs from the 82% box, where there are lots of toy frogs, you're going to say, that doesn't really tell me much of anything, right? But if you're in the other condition, where there are very few toy frogs, and the agent comes in and picks out 5 toy frogs in a row, you're probably going to say, there's probably a reason for it, right? Namely, the agent probably likes the toy frogs better than lots of other things in the world. So if you were posed with this question, in the 18%, if you were in the 18% condition, you're probably much more likely to give the agent the toy frog than if you were a kid in the other condition. Okay. And what you find is that for the 82% group, where there are lots of toy frogs and you pull out 5 toy frogs, they did not think that was informative. Right? in fact, their behavior was pretty much at chance. So they just picked randomly across all three objects that were presented to them on the test trial. And if you look at the 18% group, most of the children, about 2/3 of them, in fact, gave the puppet the toy frog to answer the question, give them the puppet the one he likes. Okay. So it's not just a matter of the puppet touching the toys a number of times, because he did that in both cases, but rather when the sample seems to be non-representative, if you like, right, it violates what you would expect in terms of physical probabilities in the population. You start to think, okay, maybe there's a reason behind it, and since there's an agent involved, perhaps there's a reason to posit a variable like preference or liking and attribute it to the agent. Okay. So under those sort of conditions, we got some evidence that they can sort of use that information to reason about a psychological state as early as 20 months also. And certainly the preschool years. And very quickly, along the lines of thinking about agency and physical properties, Lili Ma, for a postdoc in the lab, did a bunch of studies with 9-month-olds, where she presented two kinds of scenarios to these 9-month-olds. One group were in the regularity condition, where initially we just show them both the hand and the claw have the affordances of being able to pick up some ping pong balls and put it down the chute, and then it's going to roll over and end up in the small container, right? That's the top part. And then the big container is covered up and secluded, and these ping pong balls keep shooting out. And either they see something like yellow, yellow, red, yellow, yellow, red, and yellow, yellow, red a whole bunch of times, or it's just a random sequence of yellow, red, red, yellow, yellow, red, yellow, 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 right? In all cases, there are 9 balls. In all cases, there are 6 yellow ones and 3 red ones. So in fact, the probabilities are equated. But I think our intuitions are quite different. So if I were to ask you whether a hand or a claw had produced this outcome, you're probably going to say it's a hand, right? In the other case, you're probably kind of more ambiguous. It could be a hand, it could be the claw, right? So it's suggests to us that we seem to think that agents perhaps have some sort of goal in mind, and this kind of regularity is more likely to be produced by a human agent, or a surrogate like a hand, as opposed to a mechanical claw. Okay. So we compare the infants' looking times when the occluder was removed, either showing them there's a hand perched on top of the jar or a claw perched on top of the jar in both conditions. And what Lili found was that in the case of the regularity, the infants looked longer at the claw outcome, suggesting that's the unexpected case from the infant's point of view. Whereas for the random condition, there's no strong preference one way or the other. Okay. All right. If you look at work coming out of other laboratories, there seems to be quite a bit of convergence, showing that these sort of mechanisms are domain general. Right? So you can look at cases of causal learning or rule learning or visual statistical learning or property projection. And these are just a few examples that are already papers that are already published, they're already out there. So I want to suggest with these sorts of studies that infants are these little rational learners, in the sense that they're sensitive to probabilistic relations, and they can integrate prior knowledge in the form of psychological or physical constraints in their statistical computations. And these representations are robust enough, strong enough to support a prediction and action. And inference mechanisms may apply across a set of domains. I have to talk faster, I think. I will present just a few studies very quickly. I'll try to look at whether, in some sense, infants are constructivist learners early on. And we're going to go back to the case of preferences, just as we were talking about. And I want to give you a study, a mini training study, trying to address the point. So we know it's not until about 18 months of age that infants can use emotional cues for subjective preferences. So initially, they seem to assume that everybody has the same preferences as they do, right? So you give them a bowl of broccoli versus a bowl of goldfish cracker. That's a study that's been widely cited by Berkeley and Gopnik from some years ago. They themselves would choose the goldfish crackers, not surprisingly. But if you ask them what you like, they will also give you the goldfish crackers, right? And they will still give you the goldfish crackers even if you started shaking your head at the goldfish crackers and start smiling and emote positively towards the broccoli. They think that can't be the case, you can't be that crazy. Everybody likes goldfish crackers, right? But at 18 months of age, that changes. They start taking account, okay, fine, you know, if you like broccoli, so be it, right? What we decided to do is to give them some statistical sampling information to see that would be sufficient to maybe change their minds. So this is, I hope, a familiar manipulation. In one case, there are very few boring objects and lots of very interesting objects, as a mix in the big jar, or as lots of boring objects and a few interesting objects, right? And we tested the child's preference and what they think the experimenter's preference is, give them some sampling evidence, and then we test them again. Okay. Yeah, the easiest thing here is to show you the procedure.
So you're going to choose one, okay, just one. Which one? Which one?
There's some really boring white objects over there, and some very colorful ones over here. So the child says, okay, I want to play with these. And then the experimenter basically
I like to have one.
Okay,
Which one I like? Can I get a one I like? Which one I like? Purple. Purple? Yeah. Thank you for sharing.
So she gives the experimenter the same interesting object. So this is the case where there's a big jar,
That's right.
lots of boring, lots of interesting objects, a few boring objects.
6. Right? Look at this many, and they got 6 of this one.
And then she tests.
Remember, there's 2 things, right? Which one I like? Can I have the one I like? Which one I like? That one? Thank you.
So you can see the child says, okay, fine, you like the boring object, but I still like the more interesting one, right? Which is sort of the beginning of subjective preferences, right? So we don't want the child to now start to think, okay, maybe the boring ones are really interesting, everybody should like those, right? But instead, they're saying, okay, you like the boring one, I continue to like the interesting one. Okay. All right. So we tested some 2-year-olds who already know something about subjective preference, but what you can see is when the boring objects are in the minority, but not when they're in the majority, you see them giving, on the post-test, giving the experimenter the boring objects more often than in the other case. More interestingly, we looked at 16-month-olds who don't know much about subjective preferences yet, given what we know in the literature. And the effects are weaker, but nevertheless, it's a reliable difference that when the boring objects were in the minority on the post-test, they're more likely to give the experimenter the boring object. Whereas when the boring object's in the majority, then the sampling is not informative. And they said, well, that doesn't really tell me anything about your preference anyways, right? So, and this is really one-shot learning, right? So we just gave them some sampling evidence on the spot. And you can see the infants already changing their minds about what's going on, and they seem to have understood something about you liking something that's different from what they themselves like. But they will stick to their own preference, even in the post-test. Okay. So I think that's a suggestive evidence that these infants can take that evidence quite seriously. They start to kind of revise their beliefs in their heads and thinking, okay, maybe not everybody likes what I like, right? Maybe that's not a universal feature. Okay. Another idea along these trying to suggest that infants may be these constructive learners is this idea of learning to learn, also known as sort of overhypothesis formation in the philosophy literature. Basically, the idea is a pretty simple one, where learning biases could be learned by looking at the initial input, right? And so back to your jelly beans. Imagine there are a whole bunch of identical bags you see, and you don't know the contents of any of them. And somebody randomly pick out a handful from each of those bags. And the first one you see a bunch of red jelly beans, and the second one is a bunch of yellow ones, and the third one is a bunch of brown, etc. Right? If I ask you what do you think is inside the first bag, you probably say, "It's good. I'm pretty confident that it's going to be lots of red jelly beans." And for the second one, you probably say yellow, and you become actually more and more confident as the bags are being shown that each bag is probably going to contain a distinct color of jelly beans. Right? So when I show you a brand new bag and I show you just one blue one, you're going to be really, really confident that the bag is going to contain blue jelly beans. Right? That is, not only have you made what's called a first order generalization for about each bags, you actually made some generalization about the bags in general. Right? It's just a version of Nelson Goodman's bags of marble example, where you come to the conclusion that bags of marble is uniform in color. Right? That's your second order generalization. So you can, when you encounter a new instance, you're actually very, very confident what you're going to find in the last bag. Okay. And people in development have used this idea. In particular, Linda Smith and colleagues actually did a training study with young kids. So there's a phenomenon called the shape bias, probably known to most of you, that words that refer to object categories tend to be generalized based on shape and not other perceptual features, right? And you see this in robustly in like 2.5-year-olds and 3-year-olds, less robustly earlier. So they decided to do a training study based on this idea that, okay, you observe a few balls being called ball, and you say, okay, the word ball refers to objects that are all ball-shaped, right? And you observe a few instances of cups being called by the word cup, and you kind of extract the shape regularity and say, okay, the word cup refers to these cup-shaped objects, etc. Right? And you also end up concluding something like this: objects of the same label share the same shape, right? Whenever you have a count now. So that's your second order generalization. So when you encounter something like DAX you've never seen before, you will think of U-shaped objects as called DAXs and not other shaped objects when you're tested. Okay, so that's the idea. And they trained a group of toddlers, 17-month-olds, for about 8 weeks with just, I think, four pairs of objects in the lab that are very well organized by shape, and they taught them 4 novel words, right? And at the end, what they found was these babies who were trained in the lab developed a very robust shape bias that was enough to accelerate their vocabulary development outside of the laboratory compared to a group of control kids. Okay. So the idea seems to be quite feasible when you think about development. So current graduate student Z in the lab decided to try to expand this kind of idea. One is to a different domain. So this is a case where it's a causal learning domain, where there's a bunch of blocks, activator blocks, and they can activate different machines. Okay. And the design is very similar to what we've seen before, where there's a shape condition where if the block and the machine match in shape, the machine will activate, otherwise it won't. And there are a couple of categories of machines, if you like. There are rectangular machines, there are triangular machines, and there are circular machines. Right? So we just show these young kids this set of evidence. And then there's a first order generalization task where they get a new set of, they get a familiar category of machine, let's say rectangular, they get some set of new blocks. Right? You get to pick a shape match, a color match, or a distractor. And we see whether their performance will be above chance. And in the second order case, it's a brand new machine they've never encountered before. In that case, it's an L-shaped machine, and they get that's 3 different blocks to choose from as well. Okay. So we tested some 2.5 to 3.5-year-olds, and they performed quite well just after a 2-minute training session. They kind of figured out that shape match seems to be the rule here. that they succeed on both the first and second order generalization. Similarly, with the color condition, whether color match between the block and the machine was the regularity they were supposed to learn. Okay. So this is a pretty standard teaching case, where we just gave them the evidence. We want to see if they can make both first order and second order generalizations. And more recently, in turning to the idea that the child is an active constructive learner, Zia tried a version of this study where we provided the children with one demonstration, this is a little training phase, just to get them into the game. There's one activator and there's one machine, and you can see they match in both shape and color, so it's not giving away the game. And we just showed them if you put the activator on the machine, it will go off. We play some music for a few seconds. Right? We make sure the child knows how to do that, and make sure they themselves can activate the machine. And after that, we actually just left them to their own devices. So we put down on the floor 3 big bins. And the objects are grouped in this particular case. So there are 2 round machines, and there's a little activator block on the side, et cetera, et cetera. So there are 3 bins. And the experimenter basically went over to a corner of the room and said that she has some work to do, that she was going to sit down and do some work. And then just say, you can play as you like. And the 3-year-olds have no trouble with this. They're highly motivated. They'll just go out and play with the machines. And there's a comparable color conditions as well. The test trials were the same as before. And very quickly, this is a long video, so I will skip some parts. So this is just the demonstration phase to show them how these blocks and machines work.
You can do it.
And make sure they can do it.
My mom said, one more time.
Fast forward.
Whoa!
Okay. So later on, as you can see, these objects are just presented to the child.
Now, man, I have some reading to do, so I'm just going to be sitting over here, but you can play with these toys for as long as you want to, okay?
So she sits. She's actually controlling the activation of the buttons that are hidden. But this child is a pretty typical 2.5 to 3-year-old. They would just go right ahead and start playing. So when they, so she's a really good kid. So she tries it works. Or she tries it on the other one, it doesn't work. She goes to another bin, she goes out the activator block. This one works. Try it on a different machine, it doesn't work. Tries another one, so it doesn't work. This kind of goes on for a while. We gave them about 5 to 10 minutes, depending on the child's interest. So eventually, at some point, they just stop and you say, "Are you done playing?" And if they say yes, we just move on to the test trials. Okay. Yeah. So the test trials is just like the teaching condition where they were given some choices. Okay. So this is a case where we want to see if the child can, in effect, generate the necessary evidence for learning. And we were, in fact, pretty surprised how well the kids did in this study. If you look at this graph and the previous one I showed you, where we just presented them with the evidence, there are no differences between the 2 sets of results. Right? So the children did very well in figuring out how these machines work just by playing with them for about 5 minutes. Right? And a lot of them were like this girl you just saw, where they generated both positive evidence and also negative evidence. So they tried to put blocks on different machines to see which ones worked and which ones didn't. Right? And that's perhaps informative in figuring out what the rule is. All right, so I think I'm running out of time. So, very last study. Very, very quickly. I want to, again, try to get this idea of the child being an active constructive learner. I want to return to, again, the question that arises a lot in the infancy in cognition world, where people say, okay, looking time is great, but really, just because the way the method works, you're presenting these outcomes to the child after the fact, right? and the child is sort of passively sitting there watching these events. And so it's a little bit hard to conclude what they're doing exactly. Just they're reactive. That's kind of some people say about what's going on in those studies. Okay. So we decided to ask the question whether detecting a violation in a looking time study will lead to active exploration later on. Okay. So very, very quickly, these are 13-month-olds because they're good crawlers. The study is a variant of the probability study. In this case, there are 6 balls in the box, all different colors. And this is a case of sampling with a replacement. So the experimenter shakes the box, turns it over, 1 ball falls out, and you show them, let's say, the blue one. Let's put it back, shake it again, turn it over, yellow one comes out, goes back, etc., etc. Right? So either you see a variable trial where on 4 different draws you get blue, yellow, red, and orange, or you could be in a case where there's a uniform trial that every toss tosses out orange one, orange, 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 orange. Okay, lo and behold, the babies are surprised in that case. So they look reliably longer at the uniform trial than compared to the variable trial. Okay. Then we turn the task into a crawling task where there are 2 boxes that are identical. They know the contents, right? Always 6 balls that are identical. Either from this box, let's say, they'll get this set of outcome. From the other box, you look identical, they get all 4 orange ones. Right? And then we just have a choice. We put down the boxes, and they're further apart. They're pretty far apart from each other, so they have to make a choice of probably to one or the other. Right? And the baby can make a decision as to which box they want to play with. I won't show you the video, it's too long. And what you find is, in what we call the sampling condition, which I just showed you, we gave them about a minute to play with the boxes. And they spent about 27 seconds on the uniform box, the one that's anomalous and unusual, and barely any time at all playing with the variable box. Right? I can talk about the control if you're interested. So we want to use the last couple of demonstrations. These are pretty new studies in the lab, and we're still keep going with them. But we want to make the point that infants, young children often are motivated enough to kind of choose what to explore in their natural environment and what to learn. And in some cases, they may be able to learn from self-generated evidence, right? So they have the motivation and the skills to kind of generate the evidence that may be necessary for learning. And the last 2 studies are meant to address that point. All right, so just to conclude, we want to suggest that infants can acquire new concepts and knowledge using this kind of sampling evidence. And they can use those kind of evidence to learn, to acquire learned biases to guide subsequent learning. And last but not least, infants are very actively engaged in the learning process, both as infants and toddlers. All right, I won't talk about the converging evidence. Very quickly, I think there are some broader implications of the work. One is there is a metaphor. The child is a scientist that's been in the field of cognitive development for quite some time. And mostly people have focused on thinking about the knowledge structure. So you think about discussions of intuitive theories. It's a case of trying to argue that the child is a scientist. So here I think we're tackling the question from a different angle, which is to say the child's reasoning systems may also demonstrate some important properties that you'll find in scientific reasoning. And this work may also have some implications for thinking about human reasoning in general. And you might even think that young learners could be the ones who are more rational than the adults we see, given the large amount of literature on heuristics and biases that you all, I'm sure, are familiar with. And there might be implications for education practices if you're thinking about we already have some intuitive understanding of probability. It's a very hard concept to teach in school. Perhaps we could make use of that in our formal schooling. And it might also be the case, we don't have any evidence for, that developmental orders may be partly caused by the lack of these kind of inductive learning abilities that we see quite robustly in infants and young children. Okay. All right, So the take-home message is very clear that I want to argue that where we have evidence that the young learners are a particular kind of learners, namely the rational and constructivist learners. And lastly, I want to thank my students and collaborators, especially the former students and postdocs who worked on all these studies, and you just saw that I just reported. And thank you very much for your attention. Okay, so if you have any questions or comments and thoughts?
I have a question. Did you ever find any sex differences in any of your tests?
We haven't, and we always sort of look at it. That is, we do these preliminary analyses, but our samples are really small, so we don't really expect to find anything we haven't up to this point.
Do you have any hypotheses about relative sensitivity to social cues versus
I see.
cues or anything emerging?
With infants, as far as I know, even when I think about studies in literature, I don't think we found reliable sex differences in terms of sensitive to social cues, or when you think of probability as a sort of fundamental mathematical concept, whether one gender is better than the other. So I suspect the differences are not going to be found in infancy. It's possible that it will emerge quite a bit later in school-age children, maybe even in middle school-age children, for various reasons.
But even at 1 year, girls usually talk before boys, and boys walk before girls.
Right. I mean, there are some differences. So on average, they're probably more. Well, at 1 year, it's still a little bit hard to say because they're really still at best the single word stage. So both boys and girls are still, kind of struggling to kind of acquire vocabulary. It's very rare you see them stringing together words for sentences yet. Right? So in terms of first words, I'm not sure there are really very robust differences between boys and girls. So it's possible that the ages we're looking at are just young enough that we may not be able to find, we may not find those kind of differences.
In the study 6, learning to learn study, you're talking about overhypothesis function, and I think the example given was that they the infants accelerated their understanding of shape as being an important variable. But I wasn't clear to me, can you also teach them to regard color as the important variable? In other words, do they have biases towards shape at that point, or do you know what I'm asking?
Right. Yeah. So in the case of language development, so I talked about this one study that Linda Smith and colleagues had done, where they mostly focused on shape. They did some subsequent studies. I think it was Larissa Samuelson tried to train children to pay attention to a material bias. It is a little bit harder. To do. It's possible because the children already, if you're teaching a material bias, that goes against lots of the input they already have, even at 18 months of age. Right? Yeah. So we actually tried a version, so Z, the graduate student who did some of these causal learning studies, tried a version where we taught them sort of a surface pattern bias. That seems to work pretty well because they can apply pretty well to solid objects, which I think 18-month-olds expect countdowns to refer to. So it turns out that you could teach them something other than shape. So it's not just a matter of having some shape being a privilege to begin with. Yeah.
So it's very impressive evidence, and I cling to my priors tenaciously.
As we all do.
Yeah. So you and I were earlier discussing motivation, and in your concluding remarks, you mentioned sort of some of the irrational, or seemingly irrational biases in adults. Let me suggest, and it's it's cheap talk in the sense that it's easy enough for me to sit here and say, here's a baby experiment that you should do that will show that I'm right, that I should do that will show But, so, depending on what particular phenomenon you're looking at, and how much you're a nativist, there are a wide class of phenomena in adult behavior that people classify as negativity bias. That is, that negative events are more salient, more memorable, and shape behavior more than positive events. Some of my collaborators and I have a paper that's in press right now where we show that this bias applies to credulity in regard to statements about events in the world, so that people find statements that involve hazards more plausible than exactly equivalent statements that involve benefits. And both negativity bias as a general phenomenon and this credulity bias in particular are potentially explicable in terms of what you can think of as an error management strategy, which is that the costs of a type 1 and type 2 error are asymmetrical in the case of hazards, much more so than in the case of benefits. So if I tell you, don't eat the pink mushrooms, they're deadly, and I'm right and you don't believe me, you're dead, right? If I'm wrong and you do believe me, well, you just miss out on some mushrooms, right? And there isn't an equivalent asymmetry with regard to statements concerning benefits, for example. Right? So if we think about your subjects as engaging in inductive inference on the basis of a small sample of events in the world, right? All of your stimuli, the difference, either they're entirely neutral, that is the red ball or the white ball, or there's sort of an innocuous object and a more interesting object, so the black lollipop and the pink lollipop, right? So you can see where I'm going here, which is that I want to know if infants generalize more rapidly from a very limited sample of information, if the information pertains to a positive negative outcome. So, I reach into this jar and this horrible, noisy, unpleasant thing comes out, right?
Like a human subjects committee.
Well, something you can
Something
have
mildly.
right. So you can have an experimenter who shows that the experimenter doesn't feign a heart attack and drop dead. The experimenter just shows that this is a very unpleasant event, right? I think that's acceptable to the human subjects committee. So the prediction here is quite clear, which is that given exactly the same baseline information about the world, infants should generalize more in terms of induction from a small sample about a negative event than a small sample about a positive event. And that, if that's true, it seems to me that it suggests that they aren't simply attending to probabilities. And it isn't a question of motivation, because the assumption is that this is a bad thing in the world, not the preference of me versus the preference of others. Like I said, it's cheap talk for me to sit here and suggest this, but it seems to me it would be very surprising to me if infants treated, equivalently small and thus of limited information samples about the world, about hazards and about benefits as being the same. Because certainly adults don't.
Right, adults do. I think that's a great question, and I think a really interesting study to try out. And I think it's possible to come up some way where you can produce a negative outcome without, because people have done these, deception studies with kids, right? You kind of make them cry, basically, and apparently that passed. So I do think it's possible, but putting logistics aside, I think it's a really important point that you're probably right. I mean, I'm not suggesting that the baby is, they only have uniform prior, right? I don't think that's the case at all. And I think something like negativity may really be something that's that we already have pretty early. That negative information is considered much more important than positive. And there's at least one piece of evidence I know of in the literature with toddlers. So Derek Baldwin and Lou Moses did a study where they wanted to see whether negative emotion, so if you take seemingly neutral objects or something, whether negative emoting will produce avoidance, and compare it to a positive emoting, whether it will produce approach, right? But it turns out, I think, especially for middle-class American parents, they're always saying all these very positive things. It has no effect whatsoever in the positive case. But if you really frown and fearful towards the object, the avoidance reaction, and then you can measure quite robustly in toddlers. Right. So I think that's already some piece of evidence, a piece of evidence on your side to a certain extent.
Yeah, although
But
if I were to defend your position, I would say they've had a lot of experience already of being told to stay away from the outlets and you don't eat the plant and other things, and negative consequences befall failing to conform to the parents' expectations. So
right.
It's
so
consistent,
one can go a step further, as you were suggesting, which is to say maybe you need even less data in the negative case to make the generalizations, right? So one mushroom is enough because it's deadly, right? Whereas, sampling some grass or dirt is not such a big deal, right? You may get indigestion or something, but the consequences are even if it's aversive, is mild, right? So I think there's something really interesting to pursue there. At the same time, I might still cling to my prior and say, but nativity bias may also be domain general, right? So it's not just about mushrooms or poisons. Maybe it will generalize to electric outlets and various other things that we find hazardous in the environment, right? So there's a general tendency that may have learning consequences. I take that point, and I think that's a really cool thing to try to pursue. At the same time, the bias may nevertheless be domain general, such that you can learn whatever is hazardous in your local environment and really pay attention and kind of weight that evidence much more heavily than whatever positive evidence you might get.
Yeah, I mean, to a certain extent now we're discussing levels of abstraction in conceptual primitives. So if you think there's a conceptual primitive that is a distinction between a hazard and a benefit, it's a very high-level abstraction in the sense that it isn't about mushrooms or electricity or something.
Right.
And
Right. Yeah, and in fact, you might, again, I think you can build a more general framework around that. Maybe it's those kind of abstract tendencies that are in place to begin with. Like we were talking about playing with fire versus being prevented to ride a bicycle or something, or learning to eat spicy food, right? So maybe you have a propensity to say, okay, I need to acquire whatever it is, whatever has high status or that's habitual in my local culture, but it doesn't matter what it is, right? Whether it's in the food domain or in the self-protection domain or what have you.
I think I'd actually be very surprised if Dan was right about that, because the bias makes sense for an adult that's very good at sending and receiving information about dangers and things like that, and also incorporating that knowledge and using it. But a toddler is only sort of good at it, and being sort of good at receiving and processing and using information about what's deadly maybe is probably not a good thing for a toddler to do. Probably not likely to be that good, like it wouldn't be as useful. But I do think there is a part of that struck me, and that's the you're describing these as domain general, but I see them as not strictly speaking domain general, because it's dealing with artifacts, right? It's dealing with what are clearly artificial objects that maybe have a design and a purpose, and I think that they may have intuitions about the properties of manufactured objects by humans as opposed to other kinds of things that they've encountered in the world.
Well, since you disagree with Dan, that makes it a really interesting empirical question to get at, right? Because then the results will be interesting. People make different predictions. But my guess, I don't know about infants, but probably at some point, maybe during preschool years, you might start to see the negative data being more informative than others, which will also make for an interesting developmental story if that turns out to be the case, right? But I guess we're sort of thinking about, we're picking these objects partly because they're neutral, such that, if you can reason about these ping pong balls, which, I don't know if kids have maybe some experience with these objects of that sort. But you're also thinking, if you are if you encounter a tree with berries and you taste a few of those and they're all good, or they're all, you know, if you taste a handful and there are a whole bunch of good ones and a couple of bad ones, you may also think, okay, this tree in general is pretty good, right? So it could potentially generalize to a foraging situation. Or if you encounter a bunch of people from a tribe and the vast majority of them are kind and nice and they're helpful, you probably generalize to the whole tribe as well, right? So I guess I don't see, I do think these kind of situations are general enough that I'm not convinced that it's really going to only apply to small objects, right? At least that's my conjecture. Yeah. Scott?
Can you back up a slide or two?
Are you looking for something
I'm
specific?
looking for a back. Oh, 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 oh. And now we're down 3. 1, 2. Well, there's 1, 2. One more. 3.
Oh, okay.
Okay. Second bullet point, human reasoning. Second bullet point under that. Young learners may be more rational than adults. Do you have evidence from your studies that that's the case?
No, we don't have any direct evidence for that. Chris Lucas, who was a graduate student at Berkeley, working with Tom Griffith and Alison Gopnik, so they did a bunch of studies that just appeared in Cognition, where they wanted to teach kids a conjunctive rule for one of those molecular machine kind of experiments. So it has to be a conjunction of 2 objects to set up the machine. Right? It turns out that adults have hell of a time learning something that seems reasonably simple if you just tell them that that's what it is. Right? Whereas 4-year-olds are actually much better at doing something like that. As if to say, they have a whole bunch of the hypotheses that are all available to them. And they're really kind of weighing the evidence against those hypotheses. Whereas the adults had sort of skewed the probabilities, the prior probabilities of those hypotheses. They just don't think conjunctive rules apply very much. Even though the evidence tells them that that's what they should be doing, they still don't revise their beliefs in changing the probability of those hypotheses, right? So you could construe that as one case where the child is not only more open-minded, but in fact more rational because they're weighing the evidence correctly. Whereas the adults have a really hard time revising their prior belief because they say, oh, I just don't think conjunctive rules are ever going to work, and I don't believe the evidence. I'm trying to get around it in whatever way possible.
Although at a higher order, you could say the adults have just been through the process of learning correlations in the world, and in the world, those conjunctive rules are rare, and so they discount them. So they're engaging in the process that you've described just over a period of decades rather than a period of minutes.
I mean, that is a possibility, right? That is, they might have behaved the way they did because they thought, oh, okay, in the real world it doesn't really happen or something. Although I find that a little bit unusual because we do have conjunctive rules do apply in some cases, right? So I don't know exactly what sort of evidence we need to gather to show the adults really kind of learned that.
It matters what the distributions are.
Right.
So I was curious about the sort of developmental trajectories of the rational versus the constructivist features, I guess. And so it seemed like just from the overview of your studies that the constructivist studies were done with slightly older children. Is that fair to say?
Yes, I think the youngest ages we've looked at are toddlers, right? So 16-month-olds.
So I was curious whether that was done for the sort of necessity of experimental design, or whether these constructivist learning mechanisms or features seem to come in later. Particularly, I'm very curious about the sort of infants shaping their learning environment and seeking information about improbable events. Because I was curious whether you could re-envision some of the rational some of the sort of probabilistic studies early on in terms of just the head term preferences, if infants are looking longer to seek more information in the same way that the older children are exploring the more improbable bin.
Yeah, you're exactly right. So that's sort of what we want to get to, especially with the last couple of studies where the lab is developing interest, trying to look at these cases where the children can generate their own evidence. That's one sort of interesting phenomenon. The other one is one you just mentioned, where even observational learning, detecting an anomaly in the environment, is motivation enough to to go seek more information, right? So in the crawling study, basically that's what they're doing when they detect an anomaly. They say, okay, there's something going on here. What we don't know is with that sort of curiosity or exploratory drive, whether they can actually figure something out by doing that, right? So that's the piece that's lacking. So it's true that, so we use those evidence as suggesting that the child is active in the learning process, right? So it's not just like they're being bombarded with evidence and then process whatever they're getting, but rather they might, because the environment is cluttered in all kinds of ways. One of which is just too much information. You might have to decide what to pay attention to. But what to pay attention to, whether that actually leads to learning, we don't know yet, right? So I think that will be the interesting thing to pursue in the future, and I think it will work towards answering your bigger question, which is whether the constructive piece appears as early as the kind of evidence we find on the rational side.
Do you know, sorry, really quick, do you know anything about the sort of strength of learning when it's child-led, the ones say where the children are exploring the toys on their own? Have you done follow-ups? Do you know if...
We haven't. So this is the first study we've completed, and a couple of things. One is the study I showed you, the result that showed you went from, these are 2.5 to 3.5-year-olds, on average about 3. We tried a version of the study with toddlers, with 19-month-olds. Actually didn't work very well. For reasons we don't quite understand. In fact, it might be motivational. So once they learn, they know, we taught them they can put out the activator on the machine and it will go off, right? So they learn that piece. It's not they don't understand it. And then you put down the toys and let them play. Some of them just not all that interested. They will just do something else, or they go back to their parents or something. The behavior is totally different with the toddlers. And it's not that they're shy, so that's not they're clinging to their parent because they're in a lab and they're in an unfamiliar environment. It's just they don't seem to know what to do with it, right? Whereas the 3-year-olds seem to be able to kind of go quite systematically in a lot of cases to try out these blocks with the machines, right? We still try to understand what's going on with the toddlers. One thing we find very useful is if the parent is part of the learning process, it works really well. So if you just tell the parent, go now play with your child, with your toddler, as if you are at home. The process unfolds beautifully. The kid learns all the nuances, and they succeed on the test trials and everything. It's possible that kind of social scaffolding may be necessary at the beginning. That could be an important factor to consider in the learning process. But there are all kinds of other things we could do, following up on this idea that whether these kind of in the case of generating own evidence, has some advantage, because there's adult literature suggesting that there might be. So if you choose if you decide what piece of data you want to see next in a kind of relation task or something, you actually learn better than if you are just getting information from computer-generated evidence or something like that sort. It's possible we could see that kind of effect in young children. So if it's a piece of knowledge they acquired by doing things themselves, that could be different and maybe advantageous in some ways down the line. Right? Maybe it's possible these are the kids who will go on to be experimental psychologists or experimental anthropologists. They're the ones who are really, even at the beginning, show this kind of inclination. Or it's possible maybe the information will stick longer. So if you do some sort of long-term recall, it's possible that the active learning case, the kids will do better. So I think all kinds of ways to kind of explore that, and we're really just at the beginning of it.
Thank you very much.